next speaker is Lennart Döppenschmitt from the University of Toronto, and he will talk about Moduli of Generalized Kähler metrics.
Thank you for the introduction and the invitation to speak here. I'm going to be talking about this work in my PhD with my advisor Mark Gualtieri. And this is also exactly where I'm going to start the talk, because I'm going to pick up where he left off yesterday morning with this talk. So just the zeroth section is to recall what we've seen before. We've seen that if we have the holomorphic cotangent bundle of a complex manifold X, and we have a section which are local primitives of Kähler metrics, we solve them as minus I del K alpha. These are not global, so this means they don't glue. So in particular, we've seen that we can use them as local sections of the holomorphic cotangent bundle where there's a discrepancy on double overlaps. So then the solution to this, which was originally discovered by Donaldson, was the idea to reglue these patches into by a vertical shift, such that exactly this local data gives rise to a global section. And so I'm going to call this lowercase l, money it was called capital L. So this has an interesting property, namely it is not closed. It is not a complex submanifold, but it is Lagrangian for the imaginary part, because we saw yesterday that the gluing on the vertical shift does not destroy the projection. And it also doesn't destroy the property that this space has a holomorphic symplectic structure. So this space, which I drew here, that's omega, which is a holomorphic symplectic affine bundle for the holomorphic cotangent bundle. And the purpose of this was to encode this, this potential for the Kähler metric in terms of L. And we can recover the Kähler metric by pulling back the holomorphic symplectic structure. So this is a real form. In particular, it is also a 1-1 form for this complex structure. So to investigate all the metrics in this background, and remember, we view this background as the Kähler class, because this Z bundle was built only using the information of the Kähler class. So we introduce L gamma of Z precisely as the Lagrangian sections of the omega Lagrangian sections, and for now we also require that the real part is symplectic. Now I mentioned that the fiber-wise action of the cotangent bundle remains intact, and this is very important because we can use this to move any point in here, in particular a bisection. So let's take a function f. And let's view df as a Lagrangian section of the holomorphic cotangent bundle, but I only take the imaginary part of the canonical holomorphic symplectic form, which is the real canonical symplectic form. I call this little omega naught. Now this section of the groupoid acts on the section of the groupoid bundle, and we see that L acted upon by df. This is really just the sum, the fiber-wise addition. We then pull back omega. What we get is L pullback of omega plus d phi pullback of I star omega naught plus I omega naught. So I express the holomorphic canonical symplectic form as the real one. We know that this is Lagrangian for the imaginary part, so this does contribute. And for this part, we get a contribution of minus d dc. Sorry, I meant f. So we see that the motion of the Lagrangian, the im-Lagrangian bisections in the principal bundle, given by acting by a groupoid Lagrangian bisection, is exactly the motion in the Kähler class, and this moves the LS bisection in the bundle, which is the Kähler class, from this viewpoint. Now, we've already seen yesterday that the story becomes a little bit more complicated if we want to incorporate generalized geometry and generalized Kähler group metrics. In particular, this principal bundle for the groupoid becomes a Morita equivalence. So I'm still going to call this Z omega. But now, as we've seen yesterday, it has two different maps, not just one projection down to the base. So this is the schizophrenic property that Marco mentioned. And it maps in particular not to the same complex manifold on the base, but it maps to two non-isomorphic complex manifolds. And these are holomorphic. Getting the signs wrong. Wait. So we require this to be a Morita equivalence. Of holomorphic manifolds. This particular involves the kernel of these projections. They have to be omega orthogonal in Z. This involves requiring that this is a anti-Poisson and Poisson map, and these are supposed to be surjective submersions. Now, this is the replacement of the T-star principal bundle, and this is representing the generalized Kähler class. This relation was discovered by Francis, Marco, and Maxime in a paper from 2018. So this is a new viewpoint in which we use this Morita equivalence to encode the GK class. And the GK metrics in this class are still LS bisections. So this means we consider bisections of this bundle, and now it's important to call them bisections because they have to be submanifolds transverse to both foliations. And we call this space L gamma of Z. And I mentioned that I can drop the requirement that this pullback F is non-degenerate if I just called it a degenerate GK structure. So this is just an open condition, and for the sake of computations, not really important. So as you remember, we've seen that this Poisson structure is zero when we go back to the Kähler case, but in the GK case, if we pull back, what we get is this is not of type 1-1 for one particular complex structure. This is Siri. Sorry. But instead, the property is that it is jointly 1-1 for two complex structures, which are almost plus and minus. in particular, any bisection of this Morita equivalence identifies the underlying smooth spaces, but not the complex spaces. So this is the reason why I'm able to write I plus and I minus equals QF on the same underlying smooth manifold, because I have a diffeomorphism as soon as I choose a smooth bisection. It is still true that the Weinstein groupoids of X plus X minus.
Yes. What is Q?
Right. So Q is the imaginary part of sigma plus minus. This has been found by Hitchin to be an underlying smooth Poisson structure of any GK metric. So it is still true that the Weinstein groupoids integrating these Poisson structures are acting, but I'm just going to say that the action law is not linear as in this case, so we can't just add DEC of a function. Instead, the action involves flow construction. So to see what this is, I again choose a smooth function on X minus, and I'm gonna I can use.
So these are holomorphic. These Weinstein groupoids are holomorphic or smooth?
The groupoids. Sorry, the groupoids are holomorphic. The Weinstein groupoids are these holomorphic Poisson. So I'm just going to state the construction that we use Q, the underlying imaginary part of sigma plus minus, to produce a vector field of the Hamiltonian vector field, and we can integrate this by sub T, the Hamiltonian flow. Then the pair I sub T I minus FFT and Q, which is actually the data that we need to encode the GUK metric. It's still it's another GK metric for another L in this GK class for IT, the push forward of this flow, of this Hamiltonian flow. And FT is equal to F plus an integral of S by S pullback dc of I minus F dt. So you see that this is not the extra piece that I add to the to F is not just a 1-1 form for I minus, but it's that the time derivative F dot T would be a 1-1 form. But this is the nonlinear property that happens when I turn on the Q, the Poisson structure.
So for thinking of F as a smooth function on X minus is just a form of thing, right? Because the underlying smooth manifold is the same for X plus and X minus.
Right, correct.
It's just a way of thinking.
Yes, and in fact, you can even use this. I've already drawn here the target and the source. You can use this, and I'm going to call the imaginary part of omega minus little omega minus. You can use this to create a vector field V tilde F, which is omega inverse source pullback of dF. We can flow this. So this would be the exponentiating of dF SLE algebraic section, which gives us a section up here of this groupoid. And then we could compose this to move the bisection L in that space.
So the place where you lose the symmetry is in DDC, right? In DDC, you have an I minus instead of.
Right.
Because I think even Q, it doesn't depend on plus or minus. It's just.
Right. Yes. I choose here to let IT vary in fx I minus. And this, I should mention that this flow construction was first discovered by Marco in his paper on branes on Poisson varieties.
So, sorry, what is the subscript of phi in the integral? Is it
Phi sub s.
and s is the integrand?
Or is no, I'm integrating over t, but I'm pulling this back to the parameter s until time s. So I'm integrating over these pullback forms.
I think it's just ds at the end. Yeah, that's what I meant. Sorry.
Oh, sorry. Yes, sorry. Yes, thank you.
And IT phi t means what? So what is IT? Is the pullback by phi t?
This is equal to phi t inverse push forward original I plus phi t pullback composition.
That's the definition of IT.
Yes, yes.
Not IT.
Oh, sorry, I plus phi t, and this is I sub t. So I want to show with this that there's a nonlinear evolution of this structure I plus minus f and q, which is nonlinear because we have this this Poisson structure q, which is 0 in the Kähler case. Is there? Oh, this one. Okay, next I want to emphasize a particular point of view. In particular, what I want to change to the viewpoint is that I want to view that where b plus I omega are real and imaginary parts of the holomorphic symplectic form as a real symplectic manifold omega with a generalized complex brane ZB. This is a space-filling GC brane. The condition is that B and omega together form a holomorphic symplectic structure, which is clearly the case because that's where we got it from. In particular, we can upgrade the Lagrangian, the LS section, the bisection, as a Lagrangian.
Sorry, what is SF?
Oh, space filling. Space filling. We can also upgrade the Lagrangian bisection L to a Lagrangian brane bisection. In particular, what I want to define is the space B gamma Z, which maps down to the Lagrangian bisection of Z. And this is the data of a Lagrangian section. So L is as before. Lagrangian bisection of S of Z with the imaginary part. And I equip this with a flat unitary bundle. When did I start at 10 past or?
You have 10 minutes.
Okay. Okay, so why do I care about this additional piece of data? There's been work done by Jill Fine, which I'll summarize or compare at the end, to what we get. But one of the important additions is that the space B gamma as a space of Lagrangian branes is a complex manifold. When I say complex manifold, it is if-dimensional, and I'm also only working in the formal setting, so I'm not considering Banach spaces or anything like that. The best way to describe this complex structure is actually to consider the tangent bundle, the tangent space of a point L nabla to at B gamma of Z. Because this is actually the co-kernel of the sequence where I embed the generalized cotangent bundle of L nabla into TZ T star Z. And then what I get is the normal bundle of L.
Sorry, yes. What are the conditions on what you call L gamma set? Can you say that again?
L, this one.
The base, yeah. What
This is just Lagrangian bisections for Z omega. So these are the LS bisections, only that I do not require the superlactic condition. So this is just L, just the L part.
So can you say it again? What is tau?
Right. So tau is the generalized tangent bundle of the brain. In this case, for Lagrangian brain, this is just TL plus the annihilator TL. So when we view the Z omega as a GC manifold, as a symplectic manifold in the GC context, then we have here the GC structure given by omega. And because this is a GC brain, it means that the generalized tension bundle is preserved. It is J omega invariant. And so this means it in particular, it descends to this co-kernel. And this is exactly what I is.
So your matrix has to be rotated by 90 degrees.
Oh, yes. Thank you. Another way of describing this the tangent bundle, because I want to produce a normal vector field to move the Lagrangian bisection, and I want a closed one form, so I have to take actually a closed section of this bundle to move the brain data. One way to get this data is to consider closed complex one forms on X minus. So just remember, this was the diagram. And I'm mapping alpha to the normal class of omega inverse pi minus alpha real. And the one form I take from pi minus imaginary part of alpha. So I can parameterize the tension bundle of the tension space of B gamma Z at this point exactly by a closed one form.
Sorry, does the bisection condition play any role, or is it an open condition? Or?
Yeah, so the bisection condition is open, so this means it decimally, I can't destroy that just by moving a little bit.
So this is like the usual picture for Lagrangians in a symplectic manifold, but you have a
Yes,
non-convex manifold?
Correct.
With Lennart.
Yes, exactly. Okay, so now I want to get to the meat of this talk, which is a tautological construction that is available on the space of B gamma. We've already seen that this is a complex manifold.
And the complex structure on X minus plays no role. It's really what they move. Right?
So the complex structure actually, the I multiplication by I is now equivalent to multiplication by this complex structure on B gamma. So this is a particularly nice way of parameterizing this tension space. Now I want to construct a bundle over the space B gamma. And the way I'm doing this is I'm equipping every point in B gamma, which is a pair of L, nabla, with a copy of L itself. So this means I get a bundle of copies of L over B gamma. This is a logical bundle over the space of brane bisections. And I'm going to call this L hat. So this is a bisection, brane data, and a point on the bisection. Now this is everything because we haven't used yet the connection data. So we're also going to add a trivial line bundle on L hat. And over each fiber L inside of L hat, we're going to equip this with the partial connection along this fiber, which is given by the point itself. So that's the tautological nature of this construction. So we have nabla tilde, which is only a partial connection. So you can only apply this in the fiber direction, but not anywhere else. So this actually has an evaluation map into B gamma of Z cross Z, where we just evaluate this point, which is naturally giving us an embedding into Z. And this has a projection back here. So to make sense of this, so I could draw this fiber. This is the copy of C over L, and this extends to a line bundle. So now to actually complete this partial connection to a full connection, we can distinguish certain transverse directions along which this is flat. So we define nabla hat plus minus as the connections on C over L hat, such that nabla plus minus hat restricted to L, nabla is nabla, and it is flat along distinguished H plus minus. But what are these H plus minus? Well, notice that that Z has by construction two particular projections. So this means Z is foliated by the pi plus fibers and the pi minus fibers. But these fibers actually extend to the space L hat because we can compose the evaluation with the projection pi plus and pi minus. So I call this this is the kernel of evaluation composed with pi plus minus push forward. And now I should come to the end, where I want to mention a few things. Do I have 5 more minutes, or is it
Okay, page 5.
So the first interesting result is that B gamma Z, which has a complex structure, which we can think of as a GC structure, and Z has a symplectic structure, which we can think of as a GC structure. And so this product is actually a GC manifold. And what we have here is L hat, which is a manifold with a line bundle. So we can ask, when is this embedding a GC brane? When is L hat a GC brane in this product GC manifold? So it turns out that L hat, together with the average connection of these two connections that I just defined, which is 1/2 nabla hat plus nabla hat minus, embedded into gamma of Z cross Z is a GC brane. And the reason that we care about this is because B gamma Z cross Z has another brane. The same way that Z had the brane, the space filling brane B, we can now create another space filling brane, which is gamma of Z cross Z, and we pull back the space filling brane of Z and just leave it constant over B gamma of Z. So we have two branes, and what we can look at is the difference between these branes. So the difference really is the pullback of these forms, the difference between these forms and the intersection of the two branes. So this means of L hat with the curvature of nabla bar. And by the way, this is not flat. So even though all the partial connections were flat, the total extended connection is not flat. Neither pi plus nabla pi plus minus, nor nabla bar is flat. And the space filling brane pi z b, we define this and call this bolt F. And now the final theorem, if we use.
So what is B? I miss what is B? The little B.
B is the little this B.
Yeah.
This is the space filling brane that I have on Z. So I have a holomorphic symplectic structure, and I consider the real part as a brane. So the final theorem that I'm going to end with is that we can push this down, we can fiber integrate this form over the fibers L. And the result is that B gamma of Z together with I has a Kähler metric we call bar pi, and we use here the push down pi. So we do a fiber integration of this difference f raised to the n plus first power
What is N? N is the dimensional what?
n is the dimension of 2n is the dimension of x plus minus. So yeah, I forgot to define this. So the dimension of x plus minus, the real dimension is 2n. So because every L is diffeomorphic to x plus minus, every fiber here also has dimension n. And if we raise this to the n plus first power, we get 2 extra legs, and now we get 2 extra. This form is too big to just integrate over L and be a function. So we get two extra slots left over. Okay, and then the last thing I want to say in this theorem is that this actually has a Hamiltonian action. So there's an action preserving this symplectic structure of R pi by permission H transformations of C of the trivial bundle over epsilon, where this is the identity bisection of the groupoid G minus. Okay, so the reason we care about this theorem is because it's very similar to something that Joel Fine has constructed before. Unfortunately, I'm out of time, but with this theorem, we able to reconstruct, and the same as done by Fine, is to reconstruct the Calabi-Yau theorem as a symplectic reduction. So there's a moment map for this, which lands precisely in top forms, and so requiring a metric. Just remember, these are just giving us metrics in a Kähler class. Requiring that this metric has a certain top form is precisely the symplectic reduction by this Hamiltonian action. Thank you.
Question for Lennart.
Yeah, is there a way? I have two questions. Is there a way of recovering the classical nabla plus minus connections of the generalized Kähler structure from these nabla hat plus minus connections? Is there taking some sort of infinitesimal version of those?
You mean which connections of the?
If you have a generalized Kähler structure, in particular, you have a generalized metric.
Yes.
And then you have the nabla plus nabla minus connection, A plus B minus, and
this would be the omega plus minus forms with GI plus minus.
yeah, sure. There's probably a relationship there.
So these ones are not connections on the space X plus minus itself.
I know. Oh, yeah.
Okay.
I'm asking whether you can, if there is a way of comparing these with connections in the manifold itself, and whether these are reminiscent of the nabla plus and nabla minus connections on the generalized Kähler.
I'm not sure.
And my other question is just what are the zeros of your moment map?
Right. So so the moment map takes exactly this this form F, which is part of the GK metric, or just the one form, the Kähler form, and exponentiates this. So then we get F to the n mu of L comma nabla is equal to F to the n over n factorial. So requiring that where F obviously is depends on L, because F is just the pullback of the holomorphic symplectic form. So requiring that that this exponentiates to theta is precisely equivalent to saying that L comma nabla is in mu inverse of theta. That's how it relates to the Calabi-Yau conjecture.
So wait, so sorry, I missed it. So in the end, it's the equation is like that f to the n is equal to omega to the correct column or something like that.
So if you fix a certain top form theta, and on a Calabi-Yau n-fold, this might be just omega wedge omega bar. You can require the Kähler form, or in this case the GK form f, to exponentiate to that top form. And that is the same in our picture, or in the picture of Joel Fine, who did this in the Kähler case. The same is requiring that you land in the moment map of the in the levels of the moment map.
So you're thinking of it as sort of prescribing that volume.
Yes, precisely.
I see. But yeah, I mean, this is not really recovering like your like metric Calabi-Yau equation, right? I mean, there you'd want sort of like f plus to the n equals f minus to the n.
Yeah, that would be a case where you have prescribed volume form coming from some other geometric structure. Here, it's just you could in principle fix any volume form.
Right.
There's no preferred one. Yeah, just because you don't have any Calabi-Yau structure in general.
Right.
So just to make sure, you're talking about the Generalized Kähler metrics modulo diffeomorphisms or modulo this Hamiltonian flow?
So this V gamma is the Lagrangian bisections with brain data. So I equip this with the connection. So I always have this pair L comma nabla. But we saw that the Generalized Kähler metrics with correspond to just the bisection. So these gauge transformations precisely bring us back from V gamma of Z to the LS sections of bisections L gamma of Z. So this degree of freedom is what I'm modeling out by. It's similar to pre-quantizing a symplectic Kähler form and then taking the curvature back.
And out of this study, because we also have these results that you can project, right? So you're looking at moduli space of Kähler metrics, and you can say just consider one trans-complex structure or the other, and those have also moduli space. Like, do we understand also when these maps are going to be at least locally surjective? Like, go to a type of result that if you can form one, then there is a deformation of the other that keeps the pair trans-Kähler. Like, if you have this codirect go to type of result, can you get?
No. There's, I should mention this. There's work by Goto, Jeff Streets, and Apostolov, and Boulanger, which do talk about moment map interpretations of GK metrics. But at this point, it's not clear what the connection between that and our work is.
Right. Well, like you cannot project into one of the structures and see if the map into that moduli space is going to be surjected.
No.
And either for I plus or I minus, right? It's not as if you can say you find that all the deformations of I plus will be part of the Generalized Kähler.
I see. So when we modify, when we move around in the space of L gamma, we never leave the Generalized Kähler class. So this means this this Morita equivalence, which gives us the GK class. This is going to be the same up to isomorphism.
I see.
So this, even if I do this this flow of having where I send I plus, which is the complex structure here, to I have some Hamiltonian flow phi t, and I have phi t inverse push forward I plus phi t pullback. Push forward. Then this does look like a different complex structure here, but this is the same Morita equivalence up to isomorphism.
So because like I think there was some moduli space of Generalized Kähler structures in the title or something. But I should really think like the Yau's theorem, because there don't change the complex structure, just change the metric and try to get.
Yes, correct. Right? So we keep the
right.
GK class fixed and just move within the metrics.
Right. Okay.
I just like to understand a little better the statement. So you consider this space, it's finite dimensional or infinite dimensional?
This is infinite dimensional.
Infinite dimensional.
Yes.
In what sense this object which you wrote is a Kähler metric? So you wrote some n plus first power.
It is right.
Is this a differential form?
This is a differential form, and in particular, when we think about these this parameterization of the tangent spaces of with complex closed one forms, then I can write explicitly that this differential form, which is a two form on this space B gamma, formally speaking, of two tangent vectors alpha and beta, is given by alpha I.
Oh, yeah. So this is what you mean by pi star. Pi by integral.
Right, yes, I fiber integrate, and I get integral over x minus beta I minus plus alpha.
So this is some kind of generalization of the Kähler cone. Yes, so what you are considering.
The Kähler cone.
I mean, this is a space of Kähler forms in some homology, or what
So
is the analog in the
so this does
classical
not.
case? When you have the Kähler metric, what would be the classical analog?
The classical analog would be fixing the Kähler class. So we have some.
So you consider all forms in the same Kähler class. So it's
Yes.
working. So it will be some vector space.
Yes.
It's a vector space in that case. And now you have an infinite dimensional space which takes the role of this vector space. And you put a Kähler metric on it. And what do you know about this metric? Is it flat or is it a curved metric?
So if you combine I and omega, a second, I have to finish this. In particular, I have to define what alpha sum I. This is I star real part alpha minus imaginary part alpha. So if I combine omega and I, so first the statement of Kähler just says that this is a 1-1 form for this complex structure. And then if I combine omega I, alpha beta, I evaluate the GK metric. So I get something like, I might get a sign wrong, but this is G plus B inverse of alpha I plus G plus B.
So it should be something symmetric. If you say it's a Kähler in the ordinary sense, or is it?
So I would something is right formula. So sorry, I shouldn't. So I get in terms, instead of having the G dual metric, which is a metric on one forms on a Kähler manifold, on which I would just use them on these forms, I get something involving G plus B. So I have a B field in there as well. But I do get a metric on this tangent space.
Yes, is it positive definite? So it's a positive definite metric.
Yes.
Words Kähler metric, so it's positive definite.
Correct.
And compatible with the complex structure and closed in some sense.
This is a closed form, yes.
It's closed.
So that can be seen by the fiber integral directly. So if you assume that these fibers and therefore x plus minus are compact and no boundary, then the fiber integration commutes with the Durand differential. Because we fiber integrate a closed form, we get a closed form here.
Okay, then last question. So do you know something about this metric? So about the curvature of the metric, for instance?
No, not yet.
So it could be some flat Kähler metric in infinite dimensions.
Possibly, yes. Okay. Other questions?
Yes, one last thing. If I consider all the generalized Kähler structures at once, and I restrict to the series of your moment map.
Do you want to stay within the GK class?
Yeah, I would like to vary everything.
All of them.
Yeah, and so I fix a volume form in my manifold, and I consider all the generalized Kähler structures of symplectic type, which have this prescribed volume. So f to the n equals that prescribed.
Right.
Is this finite dimensional? Or maybe this is not the right modulator.
So in the Kähler case, the answer would be yes, because we know by Calabi architecture that there's just a unique solution. In this case, this is not clear, because there could even be this L gamma could have different connected components. In particular, if you have a bisection in Z, if you have this Z space, and you have one L, there's nothing in terms of the topology of Z that tells you that there isn't a completely different L prime that isn't connected to this L by a homotopy of this, by an action of a group element.
I think it's actually an important open problem, which is to determine whether the space of Kähler metrics in a class is actually connected.
I will say something about that tomorrow.
Sorry?
I'll say something about that tomorrow.
So perhaps in this formula, could you tell us where the base point is? I mean, we have some Kähler metric, okay, or Kähler form over some infinite dimensional manifold. So where's the base point?
Which base point?
I mean, you have some metric over some space. So in this space, you have the base points. If you have a Riemannian metric, it's defined at some point. So for the scalar product in the tangent space,
is the generalized Kähler structure which determines that F?
So it is hidden in this F.
Yeah, it's hidden.
Oh yes.
Yeah.
So this
means that this is not obviously some constant.
No.
I was sloppy with notation, I have to admit. So this alpha beta is only parameterizing the tangent vectors to the tangent space at a particular point.
Yeah.
And so technically this isn't the differential form, but this is the co-vector, the co2 vector at L nabla. And this is why I have this F, which is then also corresponding to this particular GK metric.
Yes. Thank you very much.
Thank you.
Very helpful.
Other questions? Okay, if not, let's thank Lennart again.